Hello everyone, I'm Tony from Intel. Today I will give a talk on CPI for runtime performance measurement, the good, the bad, and the ugly. This is the joint work with Li Yi from Intel and Jianmei Guo from Alibaba Cloud. Here is the outline of my talk. First, I will introduce the background of CPI for runtime performance measurement in cloud computing. Next, I will present our re-examination of the use of CPI in the context, along with the experimental settings. After that, I will demonstrate the prominent results and the analysis, the good, the bad, and the ugly. Finally, I will provoke the discussion on the right way to use CPI. In traditional offline performance analysis and optimization, typically a single workload instance is stressed to its peak intensity in an isolated environment. In contrast, in runtime cloud computing environments, things are quite different. There are a variety of workloads. Most of the workloads are with the varying workload intensity, and the intensity is typically low for most of the time. Those workloads are collocated together. Performance measurement in such a complicated environment then becomes a very difficult problem. Cycle per instruction, abbreviated as CPI or its inverse, IPC, is originally used widely in microarchitectural performance characterization. Since CPI is generally applicable across different workloads, it is now emerging as a proxy for runtime performance measurement in cloud computing. For example, Google's WS meter uses IPC to evaluate the performance change in a cluster after a system configuration change. It collects the IPC data for each of the workloads before and after the configuration change. A high fidelity analysis using a statistical approach is then performed between the IPC populations. Google's CPI square uses CPI to detect contentions on microarchitectural resources in workload collocation. When the runtime CPI value of a target workload deviates significantly from the historical distribution, and CPI outlier is detected and is regarded as a contention event. In the two systems, CPI or IPC values of a workload are treated as independently and identically distributed samples. We re-examine the use of CPI in the context. In short, we use two representative workloads driven with different workload intensities. In the re-examination, we look into different settings, including a case with contention on microarchitectural resources during workload collocation, a system change implicitly impacting microarchitectural performance, different settings of frequency scaling. We then report the prominent results observed in the experiment. We use the contemporary server in the experiments. It is a two-socket Intel Skylake server. There are 36 cores and 72 hardware threads in total. We use an in-memory key value store, memory cache D, as one of the representative workloads. Commonly used in cloud computing, memory cache D acts as the middleware layer in a data retrieval hierarchy. In our setting, we run 4 worker threads pinned to 4 hardware threads of 2 physical cores. The other representative workload used is SpecJBV 2015. It simulates the online transaction processing of an e-commerce store. The workload is regarded as a representative Java workload by technology companies with a heavy use of Java, for example, Alibaba. In the experiments, we start 2 backend components in 2 containers, each with 36 workers. Each container is pinned to a processor by default. For both workloads, the load generator supports varying the workload intensity. The load is generated from a different server in the same local area network with the intensity controlled. To introduce a performance change, we make the setting changes. We change the workload from its standalone run to a collocation run with a resource hog collocated. We apply a system change which implicitly impacts the microarchitectural performance. With Turbo Boost enabled by default, we disabled it. With the dynamic voltage and frequency scaling enabled by default, we fix the frequency to the base one. To understand whether the performance gets better or worse, we look into the change of tail latency under the same throughput. We also confirm the rationale of the performance change so that the ground truth is not just from the measurement, but is also explainable. We then inspect whether the change in CPI follows the change of the performance. We expect to see a high CPI value given a performance degradation. We also prefer that the change in CPI is significant. As a common metric, CPI is used mostly without the need of an explicit definition. It is commonly defined as the number of unquoted core cycles over the number of instructions retired. However, we know that there is an exception. CPI is explicitly defined in Google's CPI square as the number of reference core cycles over the number of instructions retired. Here, the reference cycles are counted with the fixed base frequency, not with the varying operating frequency. In this talk, we refer to the alternative definition as the reference cycles per instruction, abbreviated as RCPI. We first show the case where CPI performs well. Here the scenario is to run memory cache D at the workload intensity of 90,000 queries per second. We first start the workload in a standalone run. We then collocate with a resource hog simulated by StressNG in memory copy mode, pinned to different physical cores in the processor. The performance gets degraded. Though sustaining the same work throughput, the tail latency becomes higher. It is known that memory cache D is vulnerable with respect to the contentions in the last level cache and memory controllers. The contention from the resource hog is the cause of the performance degradation. While we observed the increase in both CPI and RCPI, the relative increase in CPI is higher. This indicates that CPI is more sensitive in identifying the performance impact. The second scenario may be more compelling. Here we run SpecJBB at the workload intensity of 10,000 queries per second. While by default, two containers are pinned to the two processors, we release the pinning later. The performance gets degraded after releasing the pinning. The tail latency increases with the same throughput sustained. The Linux CPU scheduler migrates the workers across the processor boundary. In today's non-uniform memory access architecture, such a migration introduces more remote memory access given the default first-touch NUMA policy in memory allocation. It then impacts the performance. This time, the relative change in RCPI can barely discriminate the performance impact, considering its large variance. In contrast, the relative change in CPI is more sensitive, just like the previous scenario. We will provide the explanation later. However, there are cases where CPI becomes problematic. In this scenario, we run memory cache D with 110,000 queries per second. By default, Turbo Boost is enabled. Then we disable it. The performance gets degraded. The tail latency increases under the same throughput. This is because given Turbo Boost disabled, the frequency drops. As we can see from the figure, CPI becomes better with the performance degradation, while RCPI gets worse. In the next scenario, we run spec.jbb at the specified workload intensity. Instead of using dynamic voltage and frequency scaling by default, now we fix it at the base frequency. This time the performance gets improved. With the same throughput, the tail latency decreases. This is because that the CPU utilization is not high in the case. DVFS then scales to a frequency much lower than the base one. However, the worse CPI does not agree with the performance improvement, while RCPI does. The explanation follows. We first explain why the change in CPI does not agree with the change in performance in the scenario with different frequency scaling. Given unhalted cycles counted with the operating frequency, one may regard that CPI is irrelevant to the frequency. Actually, it is not. Frequency plays a role in CPI. This is because that a lower frequency implies a longer cycle in time length. Then the latency of memory access measured in number of core cycles becomes smaller. Taking scenario 2b as the example, we see a lower number of cycles spent in memory latency. Core cycles in store for catch misses also becomes less. Consequently, we see a better CPI. This indicates that CPI has a bias toward low frequency settings. We then use the bias to explain why CPI is more sensitive in identifying the performance change. The worse microarchitectural performance implies a longer execution time. Taking scenario 1a as an example, we see more reference cycles per second. This means that the CPU utilization is higher. Then under DVFS, the frequency also becomes higher. Since we know CPI has a bias toward low frequency, the higher frequency here exaggerates the increase of CPI. This indicates that the sensitivity of CPI is due to the frequency change from the performance impact. Finally, we examine how CPI changes with respect to a different workload intensity. Here we drive memory cache D to an extremely high throughput, obviously with a much worse tail latency. We see that both CPI and RCPI become better. However, this should not be regarded as an attempt to improve or degrade the performance. The lower CPI or RCPI value is likely due to a more efficient use of microarchitectural resources. For example, we see less cycles stored for catch misses due to the out-of-order execution and a better parallelism. This indicates that the changes in CPI or RCPI can come from changes in workload intensity. In the last scenario, we drive spec.jbb to different workload intensities, also resulting in worse tail latency values. Again, we see CPI and RCPI changes with respect to the workload intensity. Same as the previous scenario, this is not regarded as an attempt to improve or degrade performance. Here, the change of CPI or RCPI is likely due to the significant change of frequency scaling. That is to say, changes in CPI or RCPI do not necessarily mean changes in performance. Since CPI depends on the workload intensity, the use of CPI without referring to the workload intensity may be inappropriate. For example, if we try to identify contentions in microarchitectural resources based on CPI outlier detection, in order to tolerate high CPI values under a different workload intensity, we may miss some contention cases. In those missed cases, low CPI values are driven relatively higher. Actually, in Google CPI square, diagonal patterns in CPI has been observed. However, whether the change comes from the diagonal change of workload intensity has not been examined further. If we try to evaluate the performance change in a cluster based on two CPI populations, we need to discriminate whether the change of CPI between the two populations come from the actual change of performance or inadvertent change of workload intensity. Finally, we provoke the discussion on the right way to use CPI for runtime performance measurement in cloud computing. CPI can be impacted by many factors, such as frequency or workload intensity. The use of CPI in the context can be more challenging than those described in the related work. With the same workload intensity, we may consider combining the use of CPI and RCPI. To avoid the bad, we use RCPI to comprehend the varying frequency. To leverage the good, we use CPI to exploit its bias if the performance degradation results in a higher frequency. More importantly, we need to comprehend the dependency on workload intensity. Instead of modeling CPI as an independent variable, it would be better to model CPI as a dependent variable, taking the other relevant factors as the independent variables. One may consider using a regression function as the model. This becomes the future work in the area. Here is the end of my talk. Any questions or comments are welcome. Thank you.